Hello, and welcome again from me. I'm Christian, and you saw me already in the introduction. And today we will talk about self-supervised learning. And what is self-supervised learning? And this is a quote by Yann LeCun, one of the godfathers of machine learning, who called self-supervised learning the dark matter of intelligence. So it's something that permeates everything in deep learning, but it is not so obviously visible. And you learned probably quite a bit already in the course by now about machine learning, but you haven't encountered self-supervised learning, except maybe a few hints here and there. And I also very briefly mentioned it in the introduction. And self-supervised learning really has two motivations that nicely complement each other. One of them is that training data is limited, or at least labeled training data is typically limited. You might remember the MNIST example from my introductory lecture where we talked about these postal codes where you had the scanned images of digits written on letters, and then always a human needed to sit down to to put a label on it if it's a 7 or 1, and maybe also cross verify that with a city name if it's really the correct label he assigned. And that's a very labor intensive process, so it doesn't ultimately scale. And we also talked about before that to train very large neural networks, we need very large amounts of data. You might remember the scaling laws we talked about. And yeah, this manual labeling by humans, for example, doesn't really scale up. So ideally, we would like to be able to train neural networks on unlabeled data. That's the one side of motivation. And the other side is that training a neural network for one specific task, that's very useful, but it's also very expensive. To train a large neural network requires a lot of compute, a lot of energy. And if you, for example, think again about language, we want to translate from English to French and from English to Spanish. Training a neural network for each language pair separately is quite expensive, but quite clearly, if all these networks need to share a lot of knowledge, because if you want to translate from English to French or from English to Spanish, the network needs to understand, or understand quotation mark, it needs to extract, for example, semantic information from the English sentence for be able to translate to any other language. And similarly, if you want to do a text summarization, the network also needs to extract the semantic information from the input text. And so it seems like it should be possible to, or at least it's clear that it would be very advantageous to have a network that, for example, that you can share, a basic network that you can share for many different tasks, and maybe just do a small adaptation for the translation or text summarization. And this is, the second motivation that you train for once a network, not for a specific problem, but for really more a domain or a related set of tasks. And why could this possibly work at all, that you have a network that actually works for many different tasks? And this goes back again to what we discussed in the first lecture, where I said, like, historically, machine learning worked with relatively small models that were quite limited to doing interpolation within the training data set. But this really changes with the deep learning revolution. When if you have a large neural network with hundreds of millions or billions or even trillions of parameters, we behave qualitatively different in that we generalize much better. We also looked at these examples for weather models that can give, for example, gave us good prediction of the temperature for Heathrow Airport in the heat wave outside of what was observed in the training data set, or these predictions of tropical cyclones that were new events not in the training data. The network still produced very accurate forecasts, better than any conventional model can do. So yeah, the deep neural networks, they somehow behave differently, and we generalize much better. This is also like, turn this around. If you generalize much better, well, maybe we generalize so well that you can use them for different tasks and learn maybe a common core model across different tasks. And the key concept for this generalization is what is called the feature space. If you remember, the input and the output of most neural networks is an n-dimensional vector. Right, you can think of the NLP example we looked at before, where like you have just a linear layer and an element-wise nonlinearity, but you also saw transformers now and CNNs, and we all have this common recipe that the input and output is actually simply a vector. So what you have essentially in between the different layers, for example, in MLP, is always you have an or an e-dimensional vector, how I call it here, embedding E for embedding dimensional vector internal in the neural network. So on the right, I have a more abstract view of a multi-layer perceptron with the different layers, and after each linear layer you again have a matrix, and after each point are singularities. And this vector you can interpret as a feature vector that somehow is a representation of the input data that maybe is better suited actually than the original, for example, pixel representation for your image. And yeah, so it's essentially this vector is maybe has less noise than the input because the earlier parts in the network removed the noise, or it somehow aligned the data in a different way. And it's not something really new, but at least in science we use this quite often. For example, we do Fourier transforms to extract frequency features that reveal certain structures much more clearly than the original data representation. Or we had this already also in the first lecture, we do a PCA or POD to construct this coordinate system that is aligned with our data. So the idea of doing a coordinate transformation to the data is something that is quite standard in science. The big difference here for us is that it's a learned transformation, so it's a transformation that is fitted to the data we have and fitted to our problem. Right? The Fourier transform is a method that you apply to all kinds of problems in the wide range of problems in science. And it's very effective, for example, for translation invariant problems. I have something that is time invariant to shifts in the time domain. So there's a wide class of problems where it applies well, but there are also problems where it doesn't really apply. But there is no really easy way to adapt it to. If it doesn't fit, then it doesn't fit. And you can maybe do a PCA, but maybe the PCA is also not what you want. But there's a finite number of these transformations that is available. Whereas with a neural network, right, like this transformation is fitted to the data. So in principle, if you have enough data, have large enough neural network, if you have a large enough computer, right, those are the three ingredients for our scaling laws, then you can construct maybe aligned feature spaces for quite any problem. So that's the one part, right? It's adapted, and the other part is nonlinear, right? A Fourier transform is a linear transformation. A PCA is ultimately also, once you have constructed the basis, you apply it as a linear transformation to the data. Whereas a neural network, you have a lot of nonlinearity in how the data is processed. So the mapping from the input X to the latent representation H, it's a nonlinear mapping, which is much more expressive ultimately and gives much more flexibility to construct a feature space to data representation alignment of your data that reveals the intrinsic structure that is useful for whatever you want to do. And here are some examples of the structures that you can find in trained neural networks. This is, for example, what you can see in a neural network trained for image classification. So you see that it has some intrinsic representation of shapes, and here this looks like vases. Or these are attention maps. So you remember the lecture on transformers. The key operation in a transformer is computing attention, where you relate one token to all the other tokens. And we have a vision model when a token represents typically a small patch of an image. And then the attention essentially computes some kind of similarity between different image patches. And that's what you see here. For example, if you look at the patch corresponding to a red dot here, which is on the mug, when you see the other tokens that are kind of similar, that have here the more yellowish, greenish color, these are also other parts of a mug. Whereas if you look at here, the part of a coffee in the mug, then you see what is actually highlighted here is also something more, the other parts in the image which are also coffee tokens, so to speak. And also similar here for the scissors, right? Like if you look at the patch translated to a token in the transformer that corresponds to the scissors, then you see it's also like what is similar in the attention metric in the transformer is also the other parts of the scissors, right? And so like this shows you essentially that with internal representation, each token is a vector, right? And you have a sequence of a set, more precisely a set of vectors that you turn into a sequence with positional encoding. And so this set of vectors, each of them, we are all embedded into the same feature space because we all are processed by the same stages in the neural network. You can think of having this vector space with multiple vectors in it. And then these different vectors, you compare them, right? That's really what essentially attention does. Before you do a softmax, you do a dot product, you compute the angle between the different vectors. And so you have a similarity in this feature space. And inherently, the neural network should, because attention is so central, it should kind of find vector spaces where this dot product operation you do in the attention computation to get the score matrix. But this is a really meaningful operation that extracts what is relevant. So in this sense, transformers are a really nice example for this concept of a feature space. And here's another example where we have a zebra and an elephant in the background. And again, if you take an image patch on the elephant, you see that the vectors in this feature space that are similar, that are close by, these are other vectors or tokens in this feature space, in the space. So we are close by in this high-dimensional vector space to the one token that is also on the elephant. We also see that all the zebra tokens, or the patches translated to tokens that belong to the zebra, they are also in some neighborhood in this high-dimensional vector space. And how can this work? How can large neural network models generalize? A second key aspect for this is, so the one was the feature space concept, the other one is that you learn probabilistic models. And that's a fairly general concept in modern machine learning, that you formulate your neural network as an approximation or a numerical model for such a either joint or conditional probability distribution. And if you do this in a sufficiently general manner, if you say X and Y are not something very task specific, then you get you get one of these domain specific models, what we talked about at the beginning. Large language models are again the prime example. So if you look at the original literature on large language models, you see that they are quite explicitly formulated as modeling this joint distribution over natural language, where X and Y are words or subwords to be more precise, but we can just think of it as words, X and Y. And what is large language models? Right? You feed in a sentence or a paragraph or a phrase, and what we produce as output is always the next word that you can that should come afterwards. Right? You ask a question to a ChatGPT or Claude or Gemini, you say, who won the Nobel Prize in Physics in 1992, right? And the answer is you can generate the answer by predicting a sequence of words. And this is how large language models work. So we get as input this question, and then we iteratively produce always the next word as output. And here we have a somewhat simpler task, just the house has a green, and we ask the language model to complete it, to autocomplete maybe what happens on your phone, for example, if you type, right? And then it will predict a green, it can be a green tree or a green plant or a green garden. So there's definitely some words are much more likely than other words. So, and this is essentially but the output is really this, for large language models, really this probability over the corpus of all possible words. Large language models have typically a vocabulary of modern ones of 100,000 or so different words or subwords called these tokens, but we take it as words. And the output of a language model is really a probability for each of the words in the vocabulary. And then you can take the most likely one or one of the most likely words to really complete then the individual sentences. And this is really, in this sense, really, it's this conditional probability distribution that is modeled by the large language model, because you put in some X and the output is a probability over all possible Ys. And the nice thing about language is, if you fix you have a finite vocabulary, there's a finite number of words in any language. So you can always just produce the probability as a histogram. And that's very explicitly done in large language models like this. So for every word you produce a probability, then you have this histogram, and you can very explicitly see how this really models this conditional probability distribution. But once you have this model that really models the probability distribution over natural language in itself, you can actually use it for a lot of different things, right? So you can have this chatbot, the example I used, right? You put in a question, you get back an answer. But it also works for translation. You can put in an English sentence and essentially get out a French sentence or German sentence with some either fine-tuning or some appropriate conditioning. You can do the text completion example that I already showed. You can also do, already said, you can spell out grammar correction where you have an incorrect sequence in and the model will produce a correct sequence out. Again, you will need some conditioning that the model knows what it's supposed to do with a sentence, but you could just ask it, can you please correct the following sentence? And then you put in a sentence, and then the model will likely, modern language models will likely produce a corrected output. And maybe you want to specify grammatically or orthographically corrected sentence to be more precise. Right, then you can also do creative writing, creative maybe in quotation marks, but then it turns an outline of a text into a full-fledged written out long text form of a text. So, and this is really a key concept that underlies modern machine learning and very large models, that you try to model this conditional probability distribution to get a domain-specific model that is not really no longer task-specific, but that you can use for a wide range of tasks. And here's just some examples for large language models. So this is a model that was trained really just to model this probability distribution, and in the way that I explained here, that you always just predict the next word. And the model was really trained for this. And then people, just after this training, we gave it like translate English to French, cheese. So that was the input to the model with this error. And then we were looking what is the output of the model, right? And the model indeed output fromage in this example. It was never really trained to do machine translation, but just training the next word prediction, the model saw enough examples in the training corpus to then be able to complete this task successfully. If it understood the task, that's not necessarily the question here, but it had utility in that it could do this translation without having any specific training for machine translation. And here's another example where people gave one example to kind of help the network of what it's actually asked to do. So we said translate English to French, but not only gave cheese, but gave one example of a translated sequence. And this, for example, improved the accuracy. But the important part is, again, the model was never really trained to do the task. It got this prompt post-training, and obviously it's much cheaper to just give it this prompt instead of updating the potentially trillions of trainable parameters in a modern large language model. So we just gave this prompt, and there's now this whole field of prompt engineering of how to get most of out of your language models, but just give the prompt when the model understood what it's supposed to do. So, and that's with a few examples that further improved the skill. And yeah, when this was first discovered and that this came out, had a big impact, because most people believe such kind of generalization capabilities are beyond what is really to be expected. That nowadays, a lot of most of large language models essentially, and the applications built on it, like ChatGPT and so on, rely essentially on these capabilities, that the models are able to produce good answers despite never having been specifically trained for what you want to use the model for. Good. And here's an even more complex example with full physics question. Good. So that's a key concept. We try to learn a conditional probability distribution for sufficiently general x and y to get a model that really can solve for many tasks. And then you can do fine-tuning, maybe to calibrate the output for a specific problem, but the few shot and single shot and zero shot examples show that the models really also have just intrinsic capabilities to be used for different things. And another example that is relevant for the course, we can see that actually this concept really also applies to the problems we are interested in here in weather and climate states, because we can think of what if you say x and y are atmospheric states, right? You say we know in weather forecasting we have the initial condition, and that's some computer representation of a current state of atmosphere. And we can learn the conditional probability distribution between this one state and another state. The obvious example where this applies is obviously weather forecasting, where we say X is the current state and Y is a state in the future, a few hours in the future. So, but we have many other problems. If you really learn a general distribution where just X and Y are two arbitrary states, not necessarily related in time, then we can also solve other tasks with this. If you say X and Y are just two computer representations, but maybe at different grids, at different resolutions, you can also do downscaling with such a model, because when X can be coarse representation and Y a higher resolution one. Or we can also do spatial interpolation. It's often a problem, especially with observational data, that there are gaps in the data, so you need to fill it, or if you have no gaps, then you maybe have clouds and you want to know what is underneath the cloud. So then X can be some incomplete state and Y can be the completed state. And you can maybe go think yourself through this example what other applications that you might be interested in you could solve in this way. So this idea of learning with formulating a model that learns a conditional probability distribution for a domain instead of learning just a task-specific model really also applies to Earth system modeling and to atmospheric science. And that's something, that hasn't been used a lot, but at least I wanted to highlight that this is in principle applicable. So to summarize, right, so like how large neural networks can generalize. One key part is this idea of a feature space where you, in the neural network, quite intrinsically, you have the vector representation for your input in a set of different vector spaces. After each block or each layer, you have a different representation. And essentially, by training for either a specific task or this learning this conditional probability distribution, it's intrinsically, the network will be motivated to learn a representation of vectors that kind of are well suited for solving the tasks of a problem you ask it to do. And so you will intrinsically kind of through learning get feature vector space representations that are more meaningful maybe than the input data and more suitable for the problem at hand. Right, so we saw these attention maps where different tokens needed to have similar locations in the feature space of transformers. That's one clear example. And the other part, how networks, and once you have this intrinsic structure learned in the network, it really reveals the features, removes noise, and that's something that should be useful for a number of tasks on the same data. And the other part is to really learn this probabilistic representation, where you learn some conditional probability distribution for a domain rather than for specific tasks, as we've seen for language, but I also gave the example of atmospheric states where we can also really formulate a lot of applications that are relevant in practice by saying we learn the conditional probability distribution over atmospheric states or two different representations of atmospheric states. And self-supervised learning is essentially what is used to train neural networks with good feature spaces and to learn these general probabilistic models that are domain specific but no longer task specific. Self-supervised training tasks are what enables me to learn these good feature spaces and these general probabilistic models. And why is it called self-supervised? Well, we have supervised tasks where we have xi and yi. We have an image of a digit and we have a correct label for a digit. And now we don't have labels for our data any longer. And we saw PCA was already one example where we constructed this aligned basis with just having xi. And but with neural networks, with a nonlinear training process, we have much more flexibility of coming up with a training task just given the pairs xi. But there's a one core idea that essentially underlies almost all self-supervised training, that's to hide some information from the input data. And the network then needs to predict this information. It's relatively easy. We have some sets and we can just hide it, but it becomes probably more clear if I give an example. Like one is for images. You have an image, you delete one part of the image, here for example the center square, and then you ask the neural network to inpaint essentially the removed part. So, and to do this correctly, for example in the case of this image, you see here you have this repetitive structure with the windows, And to really predict this in a good manner, the network needs to have some semantic understanding of the image. You cannot just extrapolate the color from the boundary pixels. You need to kind of get a bit of a higher level understanding of the image. And this higher level understanding of the image would be something that is useful for other tasks, for example, for image classification. And that's, again, the key part for representation learning and self-supervised learning. And here's another example where you removed, for example, a color channel. You return the color image into a grayscale image. And then you ask the neural network to predict actually the correct color for the different pixels. And again, it sounds relatively trivial, but to color, for example, the fruits correctly and the background correctly, the network needs to do some kind of image segmentation internally. Again, that's something useful for a lot of tasks, that you separate the different objects you see in an image, just so that the boundaries are clear. And the other part is it needs to have some kind of object understanding to also predict the correct color. You need to know, okay, that's a fruit, or it's a tomato in this case here probably, that a tomato is red, typically, and so you get the correct answer. So and that's one of the nice things, that with relatively simple tasks in self-supervised learning, you can train quite surprisingly effective and general models. And this, especially with hiding of information, this kind of coincides nicely with the concept or combines nicely with the idea of a transformer, where you always subdivide your input into a sequence of tokens. For language, these are essentially words you have in the language, and for images, it's the patches. You subdivide your image into patches and feed them in. And then you can always just remove some subset of the tokens. And with this, you have a self-supervised training task. So if you have essentially a model if you can feed in your data into a transformer, you can always define what is known as mass token modeling, where you just delete some of the tokens and you ask the neural network to predict the tokens. So, and here you have, again, the language example. So we have the input sequence, we have the transformer blocks that are iterated a few times. And mass token modeling in this case would be you delete some words in the middle of the sentence and you ask the neural network then to predict the missing words. And this was made popular by a paper called BERT that suggested this as a good self-supervised training objective for language modeling. And and here you get the predicted tokens, and each of them being then sampled from the entire distribution of words, as we discussed before. An alternative, and that's what is essentially preferred by OpenAI, and that's the standard for language modeling now, is instead of deleting words in the middle, you always predict the next token or the next word in the sequence. And this does perform slightly better in practice. And it's also a little bit closer to almost all of the applications where you typically have a sequence and you want to continue a sequence. For example, you have a question and you want to produce an answer. For an image, for vision transformer, so if your image is patches, you can, as I said, apply the same principle. So you subdivide your image into patches. Each patch is embedded to a token. And then again, you can remove some part of your image, and the transformer, then the task for transformers to predict the deleted part of the image. And that's similar to what I showed at the beginning, the original self-supervised task for images, but it fits just very nicely together with the transformer, where in some way you can domain independent, you can always define the self-supervised training task. Once you have tokens, you just delete some of the tokens and you get a good self-supervised training. This has also been done for the atmosphere. It's called AtmoRep, where a token corresponds to a small space-time cube for one atmospheric field. And when you have some neighborhood, this is the sequence of tokens in space and time and across levels. And then you can also delete some of the information. So we can here look at it. The three-dimensional cube is not very good to see, so we can translate it in a two-dimensional view. We have now time on the horizontal axis and space onto the vertical axis, and all the different space dimensions collapse. So we have a three-dimensional atmosphere, but we just write it along the vertical axis. And then we can essentially have all the tokens, we can delete some tokens, and the task of a neural network is now to predict the deleted information, to fill in the atmospheric states at the in-between space-time points. And here's a concrete example for divergence at a model level 96, where you see some of the deleted information. And yeah, the neural network task is now to predict this information. And yeah, this again, very easy to implement. You could essentially directly use a vision transformer to do this task, because once you have embedded the information and you have tokens, it's just mass token modeling. One of the interesting aspects for the specific case of the atmosphere here is that we get these we can also have these zero-shot capabilities. If you remember from the language example, it was like that you asked the language model directly after pre-training, and pre-training just meant you just trained the model to predict the next token or the next word. And there the zero-shot was translate from English to German or from English to French. That was the example we had. And when there was just the word and this arrow. And then the model would just, through the pre-training, by having seen a few examples of this construction, translate to the translation without ever having been trained to translate. And we have this similar zero-shot capability here, that the model can, for example, do forecasting directly after being trained with mass token modeling. And why is this possible? Well, if you think of our diagram here, right, the horizontal axis is time, and if you now mask all the tokens that are just essentially at the last time step of the input sequence, then we see that what we provide to a model is essentially this information here, the white information, the white tokens or the white squares, and what we ask the model to predict are the black squares. But that's by definition a forecasting task, and it's a subset, it's a convex hull of a pre-training task to predict randomly masked tokens. The model won't be able to generalize to something that is very different, right? But the key part is to essentially have a pre-training task that includes as special cases as many things of interest as possible, right? In the same way as in the language model, that spell correction, translation, we are all special cases of this next token prediction task. Past, future. And we can do the same with temporal interpolation, for example. That's also a special case of this pre-training where you just want to predict essentially time step in between the ones you provide as input. Spatial interpolation is the same along the spatial axis and so on. Another kind of self-supervised learning algorithms is contrastive learning. So we talked about mass token modeling. Contrastive learning much more works explicitly with this concept of a feature space, where you want to make sure that similar objects, for example, here we have two dogs, we should be at a similar location in the high dimensional feature space compared to the image of a cat. If you want to do image classification, that would be a very useful property. And contrastive learning is a method to very explicitly enforce it, that you have multiple inputs. You always try to align similar inputs and push away or have dissimilar inputs at as far as possible location in the high dimensional feature space. And here you see one instance of this, where you have two different positive inputs, or you have an anchor and a positive input. So these are two different dog images here, while the positive input is just a color changed version of the original image. And you have one dissimilar input, and you force essentially that the two identical inputs are embedded to roughly the same location in feature space. The dissimilar input should be embedded as far as possible away. So it's orthogonal or opposite direction, something like this, to your anchor point. And that's great, and that's a really good idea. The main challenge with these contrastive methods is that you need these negative and positive examples. So you need, again, it's not really self-supervised. You need some way to tell what is a negative example, what's a positive example. You see here, a positive example was just constructed by what is called an image augmentation strategy. So you just, you could also rotate the image, or here it was the color channels that were tuned or changed. But yeah, in some way you still, for the negative example, you don't get away without having some kind of labels already available. Another class of self-supervised learning tasks are Siamese networks. It's again a method that really explicitly tries to construct good feature spaces. The idea is you have one network, you similar to the constructive learning. You have two different samples. You feed them through the same network. So here we see two different networks. We feed it through, but in reality, it's the same network, and that's a key part because you want, again, that you want to train with one network, and you want that samples are embedded in a semantically meaningful way. So you have the one network, you have two samples, and then based on these two samples, we should be embedded in a semantically meaningful way. So, for example, very far away in feature space or very close together. Yeah, and Siamese network does it with a classification head. So you have an embedding that comes out of your encoder that you train here. You have this classification head. Classification head, and then you predict some kind of probability distribution over how similar or dissimilar these two inputs are. So that's the advantage is that you don't necessarily need the labels here, but yeah, and the prediction head is the discrete probability, something that typically trains very well. Yeah, with a goal, as I said, of learning a good and similar features or semantically meaningful feature space so that similar input samples are embedded close by and dissimilar inputs are embedded far away. This was used, for example, to train an embedding for atmospheric states, where you can think of this as, for example, as the ER5 data set, where we have just long sequence of states that all have the same structure, and you obviously would expect that states that are close by in time, for example, a few hours apart, are more similar than states that are far away. That's why you see here with delta t. And then essentially the idea of learning a good embedding was that inputs that are close by in time are embedded to similar positions in feature space, and inputs that are far away, they are embedded to different spaces. Yeah, and that's a self-supervised training strategy for atmospheric fields to really learn good feature spaces. And it's really self-supervised here because you only need this delta t information of where the data is positioned in time, which is available directly without having anyone to sit down and generate labels for it. More advanced, you can continue this idea. And more advanced architectures in this direction are, for example, the JEPA or Joint Embedding Predictive Architecture. That's more similar to the masking we talked about before, for example, for language models and vision models and for atmospheric fields. The key difference for JEPA is that you compute the loss in latent space. So you kind of do this masking, but instead of, for example, predicting again an image patch, you would directly compare the embedding. And that's here an example where you see here on the top, that's a masked input. You feed it through the encoder, you get a set of tokens, and then you have the same network. That's what is called a teacher network. But the key part is you feed essentially the unmasked inputs to the network, you get out tokens, and then you can compare these two token sequences. And you assume that essentially the bottom network that gets all the information produces a better embedding than the top network that just gets a small part of the input. And so when you try to get the top input, the sparse input should get the same embedding as the dense input. And this gives you a nice training task again, where you don't need any labels. You just have different masking ratios on the same input. And through this, you can then train good embeddings by forcing the sparse embeddings to be similar to the dense embeddings. There are a few tricks here necessary. For example, see here this EMA, which means that the bottom encoder, it's essentially the same network. It has slightly different weights. It's just the average of the weights of the top network over time, which tend to be, by experience, better weights, so that the bottom representation is not only better because it gets dense inputs, but it's also better because the network itself is already a bit better. And that kind of gives you that's the exponential moving average. And this is kind of this carrot and stick idea that whenever you improve the context encoder on the top, you also improve the target encoder at the bottom, because the bottom, the teacher encoder is an exponential moving average, so it gets any improvement of a train network you train, you get. And it's kind of now seems nicely to zoom into problems. So because your loss function in some way isn't fixed, the loss function itself is fixed, but your targets are not fixed. Your targets improve with actually, we get better and better during training. And yeah, this is a key and a good idea to learn powerful representations. And similar to JEPA is Dino. The two differences are, one, that the input is not a masked version, so where you have a checkerboard type input, but you have crops, so contiguous, you cut out contiguous pieces, so more like cookie cutting. And the teacher again gets small cuts, and the teacher gets, the student gets small crops, and the teacher gets the full input or a much bigger crop. And the second difference of Dino is that instead of having continuous, you look at continuous embeddings, you have a prediction head that generates a discrete probability distribution, and this, when you compute the loss in terms of this discrete probability distribution. The motivation is again that with a discrete prediction you can use cross entropy loss, and that's something that is known to train quite well. These approaches, both JEPA and Dino, we don't train so easily, because here you have the targets and the teacher and the students, or the targets and the inputs, they are tightly coupled. And if you, for example, at the beginning of a training, when essentially your encoder network does random predictions, then obviously also your target encoder, your targets will be more or less random. So you need something at the beginning to leapfrog this process. Yeah, I think it intuitively makes sense that it will work quite well once you have a good encoder, but yeah, getting it to start to converge, that's one of the tricky parts. And Dino in particular is known to be quite hard to train. So it can produce very good embeddings, and that's what you see here. And we already looked at the middle and the right example before, where essentially here, for example, all the tokens from the elephant are embedded in a similar location in the feature space, so that in this feature space, the score matrix for attention computation gives you very similar, or the vectors are located in a very similar space in the feature space. And the same here for the zebra, for example. Good, and that's another example where you get just a very good segmentation. Just the tokens intrinsically are very well separated in the feature space without you ever explicitly training towards it. But what you use is the student-teacher architecture here with this discrete prediction head. So it's quite amazing that this works so well. So summary, self-supervised learning comes from two motivations. On the one hand, you want to overcome the limit you have in terms of training data. If you require labels, there's just humans can only label so much data, and that's a very expensive and time-consuming process. And we know for the scaling laws, we want to have as much data as possible, because only if we have huge amounts of data, we can train huge neural networks if we also have huge amounts of compute. And the second motivation is to learn task-independent neural networks that are not specific to a task, but that, for example, get a general understanding of language or a general understanding of atmospheric dynamics, so that we can use them for a number of different related tasks. And most of the really powerful vision language models, we all use in some form self-supervised training. And I discussed it for large language models, where you typically do next token prediction. It's self-supervised because the next word in the text is just directly available. And for vision models, it's either mass token modeling, so you delete some patches, or you do this latent version of it in the form of Dino or JEPA, where you train the very advanced vision models are trained like this. And yeah, once you have good feature spaces, you can use the model for a lot of different things, for different applications, typically using fine-tuning. And by being able on training on these large amounts of data, because you don't have any requirement for labels any longer, you get more robust models, more powerful models that are more useful in applications.